Welcome back to the second part of our lecture series on the discussion of synchrotron radiation. In this part, we are discussing the radiation spectrum from a polar distribution of particles. Prior to this, we discussed the radiation spectrum from a single particle. We showed that it has this synchrotron F function shape, so it's a kind of a peaked function. And now we're talking about what happens when that radiation is now produced by many, many particles, and there's a distribution of those particles as a function of energy. What does the radiation spectrum look like? So for our distribution of particles, we chose a polar distribution where d and d gamma, and by the way, sometimes you'll hear it written as d and d gamma E, where the E refers to electrons, but I'm just going to, for brevity, just use d and d gamma. So the distribution of electrons as a function of their Lorentz factors is a power law between some bounds gamma 1 and gamma 2, and the index of the power law is gamma to the minus p. And so there are no electrons outside of this region. This is somewhat artificial, but there are physical reasons that this might happen. So for instance, the outer bound, the upper bound might exist because those electrons have cooled. When we talk about synchrotron radiation, you'll see that actually that does happen. Those electrons might have lost their energy and have just piled up down there. And we'll discuss this a little bit later. And then this minimum one has a little less of a physical justification, but sometimes we do see that kind of spectral peak, as we'll see that results in the spectrum, so maybe it does exist. But regardless, for our, maybe even if just think of it as a toy model, we have a distribution of particles within some bounds, gamma 1 and gamma 2, which we've written down explicitly mathematically like that. Then we have the expression for the single particle emissivity. We didn't use this explicitly last time, we will use it now. And I know I've written this with different subscripts every single time. Now I'm writing JSyn, which stands for synchrotron radiation, and now I've explicitly put in the dependencies on the frequency and on the Lorentz factor, of course. This also depends on the magnetic field and pitch angles and various such things. Not going to be relevant just now, those will be relevant later. But the things that will be relevant today or in this video are the dependencies on the frequency and the Lorentz factor. And so that's in here. How does it depend on frequency and Lorentz factor? Remember, the frequency part is in this f function, and the f is a function of x in this case, where x, again defined explicitly in terms of omega and gamma, is the ratio of omega, the observing frequency, to omega c of that gamma, the characteristic Lorentz factor, characteristic synchrotron frequency of that Lorentz factor. So again, what is the characteristic frequency? It's a function of the Lorentz factor. It's 3/2 qb over m sine alpha times gamma squared. And the most important part to remember here is that omega c is proportional to gamma squared, which we used quite expressly last time in deriving the spectrum of radiation from this polar distribution of particles, when we showed that this distribution or this relationship between omega c and gamma squared results in the spectrum also looking like a power law, where the spectral index of that power law is 1 minus p over 2, where p is this distribution. And it comes about because partly because of this relationship. And if you were watching that last video and you were wondering why I call this beta, and then there are various betas in these Lorentz and these relativistic effects, like beta is v over c. That is just convention in the field. So beta is frequently used both for the velocity of the particle in units of the speed of light, and it is also frequently used for the spectral index of the observed radiation. From the context, you usually should be clear what beta we're talking about. Is it the speed or is it a spectral index? In both cases, it's dimensionless, so that doesn't help, but hopefully it'll be apparent from the discussion. Now, when we were discussing this thing last time, I said I kind of did a little bit of a physical insight / hand-waving argument as to how we get this, and I said that if you wanted to do it more mathematically, it's a little more work, but we can do it. And so if you're wondering how you get to this using the actual integration, how you can get to it using mathematics, worry not, we shall do that in great detail now. So before we get into that, for convenience, I'm going to subsume all of this stuff into something that I'm going to call omega naught. And so this omega naught, I'm going to define, and let's also write down explicitly what it depends on. So omega naught of, let's see, b and alpha is going to be 3/2 qb over m sine alpha. So this is just a convenience expression that we're going to use because we're going to be interested in the relationship between omega c and gamma, which is of course just gamma squared, and this omega naught is just the dimensional part of that frequency that we're just going to carry around as we go through things. Later on, we're going to have to break this omega naught apart when we start integrating over pitch angles, and then you're going to have to remember that this omega naught depends upon this pitch angle. But for now, the pitch angle is not relevant. We're going to absorb that into this omega naught. Okay, so let us do this mathematically, rigorously, and show that the synchrotron spectrum actually is a power law. So to do that, what you'll want to do is, as I said last time in the previous video, we'll want to convolve the particle distribution with the single particle spectrum. And so instead of writing that kind of p omega d omega thing, let's write down the convolution explicitly. So our j sin of omega, and we're going to integrate over gamma, so it's no longer a function of gamma, is going to be the integral over this distribution from gamma 1 to gamma 2 of p of omega and gamma, right? So that's that thing, the j sin of omega gamma, I'm just calling it p here, times the particle distribution d and d gamma times d gamma. So now we are integrating over this power over the entire particle distribution. So let's put in the expressions for this p of omega gamma, which is just that. I'm just calling it something else here. And so that is going to be root 3 e cubed b sine alpha over, I have here 8 pi squared epsilon naught c m e f of omega over omega c. And then d and d gamma, which is n naught gamma to the minus p d gamma, which indicates to me that we have a typo here, and that this 16 should just be an 8. So we shall put that in here and proceed. So now this f function, which is f of x, I've just written explicitly as f of omega and omega c. Remember, this f function is this fairly complicated synchrotron function. We're going to try to avoid integrating it as much as possible, to just leave it inside the integral, and then hope that it integrates out to something magically simple, and it actually will, which is kind of fun. Okay, and then I put in the expression for d and d gamma, which is that power law, and then it's integrated over d gamma. And of course, this integral runs from gamma 1 to gamma 2, because outside of these bounds, there are no electrons, right? So we're integrating this power over this electron distribution, and so we're integrating over this range. Okay, so the next thing we're going to do is we're going to cast, because this f is a function, a mathematical function of its argument, we're going to cast this entire integral in terms of this particular argument, and that'll make life simpler because it'll become a dimensionless integral. And so we're going to cast this integral in terms of this x, which is omega over omega c. So of course the integrand will change, the limits will change. Let's look at one at a time. So what happens to the limits of the integration? So we have omega, so for gamma equals gamma 1, that corresponds to omega equals, let's call it omega 1, which is nothing but omega c of gamma 1. So that's the characteristic Lorentz factor of electrons that emitting electrons with Lorentz factor gamma 1. And when gamma equals gamma 2, that corresponds to omega equals omega 2, which is just defined as omega c of gamma 2. And by omega c of something, I mean using this expression to calculate the corresponding omega as a function of that Lorentz factor. Everything else, the b and the alpha, etc., being the same. So what x values do these correspond to? So remember, x is omega over omega c, so it's omega over omega 1. So our x in this case is, for gamma equals gamma 1, our x is omega over omega 1. And in this case, x is omega over omega 2, where omega 2 is omega c of gamma 2. Right. Okay, so now think about which of these x's is larger. So you have two gammas, gamma 1 and gamma 2. They correspond to two omegas, omega 1 and omega 2, through this expression. Each of those corresponds to an x, which is omega over that omega 1 or omega 2 respectively. And note that this omega is not an integration variable. This is just the thing that for which, this is the frequency at which we calculate the radiation. So this is just a constant as far as integration goes. So these are the two limits of the integration. Instead of gamma 1 and gamma 2, they become limits on x. So think for a moment, feel free to pause this video now and ask yourself the question, which one of these is larger, which one is smaller? Right, so you'll note that because omega is proportional to gamma squared, for larger the larger the gamma, the larger this omega, and so because gamma 1 is less than gamma 2, therefore omega 1 is less than omega 2, which means for a given omega, this x is larger than this x. So this corresponds to an x max for the integral, and this corresponds to an x min for the integral. So for the purposes of integration, this integrand now goes from x max to x min, and we will swap that in a second. Okay, the next thing to do is to deal with the Jacobian of the transformation. Because this is an integral over d omega, we're going to cast that as an integral over this dimensionless variable x. And so for that, we need the conversion between d gamma and dx. That's also fairly straightforward to do because we have x is omega over omega c, right, as a function of gamma. And that is omega over gamma squared omega naught, where I'm using this expression omega naught. Because this thing doesn't depend upon gamma, and so the gamma dependence is all in this gamma squared, and of course omega itself doesn't depend on gamma. This is just a fixed variable at which we're calculating the radiation, the frequency at which we're calculating the radiation. So then that allows us to determine d gamma in terms of dx. So I can just write this as gamma is omega over omega naught to the power of 1/2 x to the power of minus 1/2, and then that gives us the two things that we will need, which is d gamma, so we can put it in here, and the other thing we will need is gamma to the minus p, which is the second thing we will need to put in here. So feel free to pause this video here and just calculate for yourself the d gamma in terms of dx and gamma to the minus p in terms of x. Okay, so our d gamma is going to be just taking the differential here. It's minus 1/2 omega over omega naught to the power of 1/2 x to the minus 3/2 dx. Whereas this gamma to the minus p is just this thing to the power of minus p, and so this is omega over omega naught to the power of minus p over 2 x to the power of p over 2. And you can start to see pieces of this now appear in this Jacobian. Okay, let's put all of this together. So this integral then becomes, let's see what's an integral over. So it's an integral over gamma. So anything that doesn't depend upon gamma can be pulled out. This stuff doesn't depend on gamma, right? So this stuff down here doesn't depend on gamma. This omega doesn't depend on gamma. It's the omega c that depends on gamma. So that's where we have all of this x Jacobian business that we're doing, and does not depend on gamma. This gamma to the minus p is going to get replaced by this, and then we can pull this out, and so we'll end up with the various powers of x inside the integral. So here is what that looks like. So it's √3 e cubed b sine alpha over 8 pi squared epsilon naught c m e times the integral from x, and so we remember this is going to be from x max to x min, and then there's this minus sign here, so we can flip this integral over to be from x min to x max, and then we have this f of omega over omega c, which just becomes really conveniently an f of x, which we can just close our eyes and just leave inside this integral. And then there's this n naught, let me just put it in here. So it's n naught omega over omega naught to the 1 minus p over 2, just so you can see the pieces, x to the power of p over 2. And then I'm going to just write this down here, but it's part of the same integrand, 1/2 omega over omega naught to the power of 1/2 x to the power of minus 3/2 dx. Right, so just to highlight where all of these little bits and pieces came from, this bit comes from the d gamma, right, it's this thing, and then this bit comes from the gamma to the n naught gamma to the minus p bit. So this part is just gamma to the minus p. Okay, so now we are ready to do this integral. To do that, we can pull out the things that don't depend upon x, because now this is an integral over x, right? So anything that doesn't depend upon x, we can pull out. So I am going to write that here. So our Json of omega, which we'll put down here, and I recognize that because, let's see, I think that might help, or maybe not. I'll move aside when we've finished writing this. So there is a factor of a half, so that becomes √3 e cubed b sine alpha over 16 pi squared epsilon naught c m e. And then there is this n naught, which is just a normalization for the total number of particles. And then we have the interesting stuff. So let's pull out. So this integral is over x, and it doesn't depend on omega. Omega is just a fixed value at which we calculate the spectrum. So we can pull out all omegas. Omega naught doesn't depend upon x, so we can pull out the omega naught as well. And so we have the most interesting part is already done. We have omega over omega naught to the power of 1 minus p over 2. And then we have this integral from x min to x max of f of x, x to the power of p minus 3 over 2 dx, where I've just collected all the powers of x in the integral. Okay, so this final expression is the expression we are looking for. It may not seem that way, but it has all of the relevant information, because now this tells us the radiation spectrum for a Polynomial distribution of particles in its full glory. And we have the normalization factor, which is just a single particle power times the number of particles times the spectral bit, which comes about from integrating the polar distribution. And this bit, which we had earlier, is the same. This bit over here is the same as this bit that we had earlier. So in other words, we have now kind of rigorously derived the power law spectrum from its polar distribution of particles. What about this? Well, okay, so we'll discuss this in some more detail in a little bit, but this integrand doesn't depend upon frequency. Really the only part that depends upon frequency, actually, what part depends upon frequency? So have a moment to think about what part of this integrand depends on this integral depends on the frequency. And the answer is it's the limits of the integration that depend on the frequency. Because remember, this x min and x max have an omega in the definition of x min and x max. So our observing frequency sets the limits of this integral. And for regions where we are interested in here, between gamma 1 and gamma 2, we will see that we can basically expand these limits out of this integral from 0 to infinity. And when we do that, this whole thing just becomes a p-dependent number. And there's no omega dependence in this expression anymore. And so we're going to, in the next little discussion, the next video, we're going to discuss how we can take a few different limits of this expression in different spectral regimes, and how that gives us the different power law regimes in the synchrotron spectrum. But what we've done here is explicitly integrate the single particle spectrum over a power law distribution of particles, and show that it looks like a power law times a correction factor. And that correction factor becomes interesting, as we will see in different spectral regimes. So that's going to be our next video.